Can you see the slides?
Yes, now you can see them again.
Giacomo?
Yeah,
Can you hear me? Okay.
yeah.
Okay, good. Okay. Okay, thanks. Thank you everyone for joining us today. I'm very happy to introduce this webinar. I'm Francesco Granella, a researcher at CMCC at the SEME division. And I'm happy to introduce the speaker, Giacomo Falchetta, who is a research fellow at the ECIP division of CMCC and affiliated scientist at IASA. Giacomo is an energy and environmental economist with a strong multidisciplinary background. He has worked extensively on energy poverty, the effects of climate change impacts on energy demand and supply, the water, energy, food nexus in developing countries. And for as long as I've been knowing Giacomo, he has been working extensively with the data analysis. I guess he's quite expert in the field, as we will see today. So before we get started with the webinar, let me just introduce CMCC. CMCC is a leading research center focused on understanding the interaction between climate change and society. It provides reliable, vigorous, and timely scientific research to stimulate sustainable growth trajectories, protect the environment, and develop science-driven adaptation and mitigation policies in a changing climate. Disconnected. Okay. So CMCC is a foundation. Its founding members Research Institute and University and allow expertise within and across disciplines. CMCC is organized in a network of thematic centers and research groups distributed throughout the Italian peninsula. This network organization strengthens the ability of the center to connect public and private entities and to develop multidisciplinary studies across research topics. The interdisciplinary focus is indeed at the core of CMCC, and it's built in its scientific organization. Also very involved, putting considerable resources in the dissemination of the scientific article its scientists produce, but also through educational programs, events, and communication activities for the public at large, like this webinar. Researchers at CMCC can avail themselves to the Supercomputing Center, the most powerful computational facility in Italy dedicated to climate change, and one of the most advanced in Europe. Before we get started, a little bit of housekeeping. Your audio and video will be deactivated by default. If you need to intervene or you want to ask questions, you can either write in, we highly recommend, or you can use a raise hand feature at the bottom of the screen, and I will give you the floor. We prefer to keep this practice for the discussion at the end of the webinar. A final remark, this webinar will be recorded and will be uploaded on the YouTube channel of CMCC. So without further ado, I'm happy to leave the floor to Giacomo for his seminar on machine learning and big data, applications from individual to societal level adaptation. Giacomo,
Thank
the
you.
floor is yours.
Thank you very much, Francesco. Thank you very much for the introduction. Let me share the presentation. Can you please confirm if you see my screen?
Just a second. Yes.
Okay, thank you very much. So good afternoon, everyone, and welcome to this webinar, which, as Francesco just introduced, is dealing with topics of machine learning and big data in the specific context or applied context of looking at different dimensions related to climate change, and in particularly thinking about adaptation on a multi-level scale, so from different points of view and from different, let's say, levels of society, from families, individuals, society, and policy, as we will see. So just to provide a little bit of background, the recent working group through contribution to the IPCC 6 assessment report clearly highlighted that human-induced climate change has caused widespread adverse impacts and related losses and damages for both nature and people beyond natural climate variability. And also it highlights that some development and adaptation efforts have reduced, indeed, vulnerability successfully. This comes from the summary for policymakers of working group 2, 6 assessment report. So as you can see from this chart, the main idea here is that climate change is impacting society at large on a broad number of different levels, starting from the left side of the graph. So let's say from very micro level, that is to say people, and when we look at society, let's say we put this moment the focus especially on society more than the impact on nature itself. Then especially starting from small micro levels, so like households and families and people, and then with growing, let's say, zoom out, going to a mesoscale, that is the scale of infrastructure, of land use decisions, of the dynamics, let's say, that connect together different households, different individuals, so the social dimension, the social capital and network dynamics. And then up to the macro scale, that is to say the scale of the macroeconomy, for instance, the scale of justice and inequality, and the scale of policy, which then connect, let's say, to the global dimension of climate change. What is important to highlight is that this type of zoom in, zoom out from micro to macro is bidirectional. So it's on the one hand impact of a global phenomenon as climate change onto a different number of dimensions, from macro to meso to micro, but also the response and the interaction of the responses from the micro to the meso to the macro that determine the level of these impacts and the extent to which adaptation to a phenomenon like climate change is effective. This type of impacts are, of course, generated through a variety of channels, and through their interaction at these different levels, then what is effectively observed as impacts is determined. The challenge is that given that this both vulnerability and hazard, and also risks and adaptive capacity, are after all generated and shaped by interaction of global phenomena, so climate change for sure, but also other global phenomena of social demographic change, of economic growth, and so forth, and highly local factors, so factors that are really context specific. And this, let's say, heterogeneous set of levels that are interacting together in determining the impacts of climate change is revealing as challenging for studies that aim to assess these dimensions and produce some, let's say, also projections or some estimates of these phenomena for larger regions, so for what matters after all at the level of decision-making and policy. So on the one hand, we had, for instance, macro models like integrated assessment models, which, despite recent efforts to really try to improve their representation of adaptation as a complex and nuanced phenomena, still they have, let's say, limitations in their capacity to capture this variety of scales that are at stake when dealing with climate change impacts and adaptation. And on the other hand, we have a broad range of highly context-specific analyses that are really, let's say, fit for purpose for specific contexts, but however, they are really limited and challenging to derive generalizable knowledge from, given their study design, which tends to be very local. So in this context, what I'm arguing here and what I will try to discuss a bit in this presentation is that it's really important to try to understand how different levels, so from the micro level to the of individuals and households to the meso level of, let's say, a local context, such as the context of a city, for instance, and its infrastructure and local setting, and up to the macro, that is to say, country and global factors, interact in shaping these relations and in determining impact and adaptation decisions. So in this webinar, of course, to tackle this significant challenge, there is not a silver bullet. There is not only a single approach that is effective in doing so, but what I want to emphasize in the duration of this seminar is the potential supporting role of methodological aspects and evidence-based understanding of these of different phenomena concerning these spheres, and in particularly through the use of the wealth of available microdata, that is to say, data that is really, let's say, granular and disaggregated and context-specific, which it includes different types of data, from survey data, so like microdata of households or individuals or companies, so disaggregated data, up to geospatial data such as GIS archives and data collection repositories, up to satellite imagery, so like big data that is collected for large geographical areas but with a very high level of disaggregation, and how this emerging ever-growing wealth of highly specific data can be put in relation with big data modeling and empirical techniques. And here the emphasis will be very much on machine learning as a tool that can extract knowledge and create a better understanding, let's say, at a general level, but starting from highly specific, highly localized information. Why machine learning? Just a few words. Because machine learning, it's a very flexible, let's say, modeling environment, data modeling environment, which is potentially able to capture complex relations among data, which are not always necessarily intuitive or detectable by, let's say, a traditional process-based understanding of things. And also because it allows to estimate highly heterogeneous impacts and pathways at multiple levels. So it's very flexible to different type of applications. And despite its limitation that maybe we will discuss a bit at the end of the seminar, for instance, the fact that it's not the best tool to produce point estimates. However, it has a strong potential contribution when it comes to generate predictions and projections of phenomena and things, given this flexibility to classify, estimate, cluster, and put into relation different things and phenomena. So this webinar will, however, be quite applied, so it won't not focus, let's say, on the theory. This was just an introduction, a background. It will provide two very concrete examples of research that, together with colleagues at CMCC, we have been carrying out in the recent months, years, which, however, are, let's say, examples of how this big data and machine learning can be applied to study topics relevant to adaptation at different scales. The first one will be focused on microdata, so on household survey data, to analyze the air conditioning as an adaptation response to heat, to cope with high temperatures. And another one will be instead focusing on the application of machine learning for modeling satellite imagery to assess urban green space, which is something which I would put, let's say, in the mesoscale of the framework I was presenting before. So it's not a individual or household decision somehow, but it's something which is happening at a context level, so like city level, but it's after all shaped by policies. And after all, in the end, I will try to bring a general discussion based on the example of these two applications. So without further ado, let me jump to the first one, which is a piece of work which is under review, so it's not yet published, with the co-authors from CMCC, and not only. So just to give a bit of background, energy demand for cooling adaptation is perceived and widely accepted as an increasingly crucial topic for global energy policy and decarbonization efforts. Not by chance, there was a report by the IEA a few years ago specifically on the topic, both because climate change is increasing heat exposure and therefore making cooling ever more relevant, and also because of big global socioeconomic transformations that make this type of technologies more accessible, more affordable, and more desired also. But this has important implications for the power system, given the high energy intensity of cooling appliances. And of course, as a result, also the potential feedback CO2 emissions that might be caused by the use of air conditioning in systems that are not yet fully decarbonized. So it's necessary, it's very important for many decisions to understand how cooling will be adopted and used worldwide. But the challenge here, also to connect with what I was presenting before, is that cooling is a very context-specific phenomenon, because it stays at the interaction between climate and environment. So let's say factors that are, so to say, external from the sphere of local decisions, but then it also involves very local factors such as income, education, other social determinants, as well as building decisions and policies and so forth. So this study seeks to generate models based on a large pool of household survey data that I will be presenting shortly more about. Tries to understand from a global pool of household survey data what are, first of all, the key determinants of air conditioning adoption, and then its utilization, that is to say the consumption of electricity for cooling, and then to derive projections into the future of these transformations, but always trying to keep a very, very careful eye on the local dimension. So not just looking, for instance, at very large scale, but trying to keep a local focus also when generating projections. This is a bit the methodological framework and the data. So in the top right map in orange, you can see the number of countries that are covered by the pooled household survey dataset that we put together. Sources are the statistical offices from different countries that carry out socio-economic surveys in different countries, covering crucial information that is important for us, which is the availability of air conditioning, the ownership of air conditioning in families, and their energy consumption and expenditure, as well as a set of other socioeconomic and building stock determinants, together with climate data, so the historical localized climate data for each household survey or the region where these houses are located. And then the idea of the framework is to carry out the models that are schematically presented in the equation down there. So a first stage model to predict the probability of air conditioning ownership for a given household as a function of different drivers, including climate, so temperature-related metrics, economic drivers, socioeconomic drivers, and so forth. And in a second stage, the electricity consumption as a function of all the drivers of the first stage, including then also the air conditioning as a driver per se to understand its impact. And then after all, using different future projections of climate and these determinants to derive something which resembles the map that you can see on the top left, on the right, bottom right, which are, let's say, maps of the predicted ownership and intensity of use of air conditioning, very aware of the local context, so very geographically disaggregated. I won't spend too much words on the data that we use, but this dataset, multi-country household dataset, is quite large. As you can see, it puts together several countries, more than 650,000 observations. And then it includes all a set of variables which I was presenting. And then we parse this with projection driver data in a gridded fashion, following the SSP LCP logic of the APCC for different scenario to project the evolution of factors into the future, and then to predict, project the future evolution, show output data as described here. But of course, first, it's important to verify that the model is valid. So we train this model. In this case, we train a random forest model after having tried other simpler specifications, starting from a parametric model like an OLS, or then something a bit more flexible like a GAM, so generalized additive model. But then we clearly observe that across many metrics, the random forest non-parametric classification and regressions are more effective. And we show here through several metrics. On the top row, you have the first stage, which is a classification problem, AC or not AC for a household. And on a bottom level, you see the regression model to predict the intensity of electricity consumption. And so we do the conventional training and testing set split, and we consider several metrics that overall point at a rather satisfactory capacity of this large model to predict the status of a household in these dimensions. Maybe two things I just want to highlight is, first of all, the importance of using the right metrics to evaluate the model. For instance, in the top row, you can see the kappa metric receives particular emphasis because the kappa metric is able to account for the fact that the classification problem is unbalanced by the fact that there are more people without AC globally than people with AC globally. So we might want to avoid using metrics of accuracy that may overestimate the predictive power of the model because the two classes have not equal likelihood. And then the second thing maybe I want to point is that we then move to a regression problem. So in the regression problem, we consider different indicators which are more suitable, let's say, for the continuous choice that the model is trying to produce. We also want to check for the external validity. So this first step was, let's say, to carry out this cross-validation, but at the level of households, so at the level where we produced we estimated the model, but then we want to try to also check what it implies to aggregate this household level information to reproduce them, reproduce statistics at the country level, as these surveys are nationally representative, and compare them with statistics from different sources that report, for instance, the AC penetration rate for a country, And this is a second, so to say, validation step, or we can call it also consistency check. And of course, this is still work in progress, not yet published, but it's interesting to see that somehow also when aggregating the results, we seem to find some good consistency, some capacity of the predicted values once aggregated to mirror some official statistics from different sources. So then we proceed to producing some projections, as I was saying, the importance of the local context, so the use of local data for projections, gridded downscale data for climate change, for socioeconomic evolution. And so this allows to appreciate, let's say, that not all countries have the same evolution, not all regions evolve the same, and even within countries there are big differences that are shaped by the heterogeneity in the conditions and in the response to air conditioning adoption in the countries. So this is just an example for different scenarios. How do we foresee the evolution of phenomena? And then, of course, one can aggregate to regional trends, which is something maybe more conventional, which we are more used to see. So let's say aggregating to projections that are summarized at a different scale, but of course starting from this gridded projections. So it's really a matter of choice of which is the scale of interest to show the results for. As this is all these applications are, let's say, examples, I will not now focus a lot on discussing the results themselves. It's more examples of this story of using data and models. So if you have then questions about the specific results, we can discuss them later in the discussion. But yeah, just in one sentence, what you can see is a soaring demand for air conditioning in many regions, but also inequalities in how this happens. The same we do for consumption, so consumption levels, and aggregation of future consumption along projections, and similar story, a huge boost in the electricity demand for cooling in different regions, with some very, very evident emerging hotspots. You can see, for instance, the northern part of India emerging as a major hotspots, also Nigeria, and also China showing a huge boost in electricity use for cooling. The nice thing that maybe it's also worth pointing out when it comes to impacts and adaptation is that these granular projections, so by their own nature, they allow for a very disaggregated understanding of the inherent inequalities that exist within countries, across countries, in different income levels, for instance, on the left panel, or really at for every different household on the right panel, in terms of how cooling will grow in the future and how it will be unequally available among different types of households in different regions, which is something I think important when it comes to focusing on vulnerability, on adaptive capacity. So something which is much more detailed than, let's say, a country level or a regional level assessment, which might really hide a lot of inequalities inside the statistics. So to summarize this study, how it can be used. It can be used, this output data that is generated, and it will be publicly available as soon as the paper is published. But the idea is that it can be beneficial as an input in different type of analysis in energy modeling or integrated modeling. It can provide the heterogeneous impact of climate change on cooling energy demand for specific groups of people, which can be a regional disaggregation, it can be a income quintile disaggregation, It can be an age group specific disaggregation. So depending on the study that one wants to carry out, this type of flexible model can allow to produce estimates for a large number of groups and disaggregation. Also, probably this data is potentially suitable to be used in studies dealing with health outcomes and mortality impacts in relation to climate change, and also in relation to the role of alternative cooling solution, such as urban green space, which is the topic of the second example that I would like to bring here, which is a manuscript still in preparation, so work in progress, very preliminary. Why urban green space? Because it's considered an ever important indicator for evaluating the environmental and social sustainability of city, because it has many benefits. Some of the most salient and interesting for our discussion here is that it reduces health impacts, and also it has potential to reduce energy demand in buildings due to its contribution to reducing the urban heat island effect, and then a broad range of ecosystem services, reducing the impact of floods and making people overall feel happier also. So in this context, we also apply a machine learning model. In this type, it's a gradient boosting model. So it's a, let's say, enhanced or modified version of a tree-based algorithm like a random forest in the previous example. And here the training data are mostly satellite imagery, so multi-spectral images captured at a high frequency and with a very high spatial resolution from the space, and also some ancillary spatial information such as climate records and socioeconomic and infrastructure level, with the objective of predicting street level urban vegetation density, starting from a set of given labeled data, to then come up with a model that is able to produce estimates of urban green space availability in different areas, in any, say, custom area, required area of the world where the training data is available, but the satellite imagery is available virtually everywhere. So this means virtually everywhere, and understand what's happening with urban green space around the world. The training data is coming from the MIT Treepedia, which is a project that mapped in a number of cities, which you can see plotted on the map. The density of canopy cover in cities, within a set of cities of the world, with a very high level of spatial detail, as you can see on the example of London on the right-hand side. I won't go too much into the methodology of how this was produced, but it was produced through street-level imagery, so like photographs like Google Street View taken on the road. And then to do this, we consider here Sentinel-2 mostly as the main training data, so multi-spectral satellite imagery and climate information with Area 5 data and additional data. And we use Google Earth Engine to process this big amount of geospatial data, and eventually we carry out the statistical modeling in R. Similar to before, very important to show the capacity of the model, the external validity also of the model to perform on a training set and then on a test set of previously unseen observation. And also important to consider the fact that observations are spatially explicit, so we may want to consider the spatial dependence among them, so considering methods of spatial cross-validation that is aware of the geographical location of observations. And as you can see here, we also are able to reach a pretty good level of accuracy in reproducing this vegetation canopy cover index, which is measured on the street level, from data that are instead coming from satellites. around 75% are square on the training set, 68% on the test set, which then altogether brings back the full model to 75% accuracy. And this is interesting because once the model is proved to be valid, it can be used to produce estimates of urban green space in a much larger number of cities than what was available in the training set. And here you can see we carry out an assessment for a number of large cities around the world. And you start, let's say, from an assessment based on what you can see in the zoom, which is the city of Rome, for instance. So you can assess in different areas within the city of Rome what is the estimated density of urban space. And then by computing some spatial statistics, you can come up with a metric of the average urban green space in the city, which is what you can see from the color legend in the map. Again, not too much focus on the results in this webinar, but the interesting thing is that you can then track, again, as I was showing in the previous presentation, at different scales. So from the city level, which you can see in the right panel, to then the aggregation in the regional level, which you can see on the left panel, and try to see what is happening in urban green space around the world in different areas. And what we find is that over the last, let's say, 5-6 years, we observe a mild decline in the urban green space at a global scale. But then this is different between regions, as you can see. So to wrap up with this second application, why is this interesting and relevant to application, in relation to application with climate change? Because urban green space, according to a large literature, which is, however, a very local literature, maybe case studies on cities, has an association with energy use in buildings, particularly for climate and cooling. So trying to get a general picture of urban green space around the world can also help to understand what it implies for cooling needs and what different policies to expand urban green space might mean for energy use for cooling. However, there are several more dimensions that can be explored. There is a dimension of reducing the impacts of floods, a dimension of environmental justice also, so how equally a green space is distributed within a city, if it's let's say not available to all social groups equally, and then also if it can provide some benefit for health and reducing heat waves impacts on health, for instance. These are just applications that are possible, let's say, relevant to this study. Just to show one last slide on this, we are trying to assess if and to what extent urban green space can reduce residential energy demand. And here, this is a very, very preliminary graph, but the idea of trying to synthesize this urban green space assessment, maybe at a country level, and put it into relation with energy balances to see if and how urban green space can mitigate energy demand. Take this graph with a grain of salt, let's say. So it's just very preliminary, but the idea is potentially to try to identify relations between urban green space and energy use, which can then be also maybe implemented into models. Okay, let me jump to the conclusion very quickly about these two applications. So the main general conclusions are that machine learning data modeling techniques have, in my opinion, the strong benefit of supporting the understanding of the impact and future prospects of different climate change impacts and adaptation phenomena, actions, and infrastructure, and that large-scale microdata, so data that are disaggregated, especially connected one with another, so survey data with geospatial data or climate data, really can provide important insights to better understanding phenomena at different scales. And some of the limitations that are always presented by some, but brought up by some discussant when we have presentations about machine learning methods, like black box nature of machine learning, can and are partially being overcome through novel approaches and ideas of how to better, let's say, deconstruct what is happening inside the machine learning model, and altogether also by the fact that the parametric coefficient estimation of linear model, of parametric model, is not always a necessary requirement, especially when we deal with prediction and projections, where we can produce projections for different heterogeneous groups and settings. And so in the future, this type of applications are suitable, I think, for understanding how different levels that I was presenting at the beginning of the presentation can interact and mediate between each other to determine impacts and adaptation. And the big questions still to be addressed is then how these type of methods and analytics can be properly integrated into modeling studies. So these empirical insights can be integrated then into models such as the integrated assessment models. I will stop here and thank you everyone for the attention and give back the word to Francesco.
Thank you very much. Thank you very much, Giacomo. Both papers are very interesting. So I see one is being submitted, the other is still preparation. I'm looking forward to reading them. I really appreciated also the introductory framework that you gave when combining the micro level with a more global perspective to uncover what happens at the meso level. I think it is very useful, and more generally, I think these what you did with your co-authors is a very nice template on how to combine machine learning and geospatial data on one side, and basically making climate projections into the future with different scenarios and using machine learning basically to estimate these damage functions. So I'll think I see some questions in the Q&A, but perhaps I'll just break the ice with one question myself. So in both cases, you were training your algorithm on a certain number of countries or cities, and then you predict the vegetation, green vegetation index or AC penetration also for other countries and other cities in the world. So basically you're extrapolating, right? So I was wondering what precautions did you take with an eye to the external validity of your sample? Because I presume, perhaps you had developed country a bit more represented than developing countries, but yeah. So I was wondering what measure did you take thinking about external validity?
Thank you very much, Francesco, and I think it's a great question to break into the discussion, and also indeed a big challenge. Maybe I have two things in mind, that two type of actions and reflections that are important in this context. One is more qualitative and descriptive of the data. So when you are dealing with a given data set that you want to use, it's really important to try to think and look in the data if you believe there is some selection bias, so to say, in the data, or under or over representation of different things, which can be countries, it can be climate conditions, it can be other factors. So really to get a sense of how your data is able to represent the whole spectrum of situations that then exist or will exist in the future, maybe due to evolutions of climate, of society, etc. So first, really look at the data to qualitatively get a feel of what is the situation. And then in a second step, of course, try to use this type of validation approaches, which is, let's say, the most common is cross validation, so leaving out some observation or some samples from the original training of the model to then validate the model on these left out observations. But what I point out in addition to this is that this cross-validation often is more effective if it's stratified. That is to say, you just don't take completely random observations out, but you take perhaps random observations, but with care of grouping or weighting by the fact that some countries or regions or setting might be overrepresented. So doing some type of stratified sampling in the cross-validation can ensure a better representation of underrepresented entities. Yeah.
Yeah, there's a very interesting. Yeah, thanks a lot, Giacomo. So I'll move to the Q&As. There's a Johannes Emmerling asking if the model deployed allows to identify certain drivers for specific results. I think you mentioned this in the last slides with the interpretable machine learning, right? So maybe you want to just spend a couple of words more. Johannes also asked, in particular, why is, for instance, air conditioning adoption fairly similarly distributed by mid-century? But electricity consumption is very spotted, with hotspot in Nigeria or northern India. So I was wondering, like, why the discrepancy? Can these interpretable machine learning tools be used to identify these discrepancies?
Johannes, tricky one, but I'll do my best. So on the one hand, in the interpretable machine learning toolkits, I think probably econometricians or people who are used to see comparative estimates of effects of different drivers might appreciate something like the Shapley values, which is an approach to get a sense of how different drivers, depending on their level, influence the predicted values based on the machine learning model. That is to say, to get a sense of how different drivers and their values are important to the model and in which direction they move the result of the prediction. So this type of metrics that exist, they are not, let's say, a one-to-one match with what is like, I don't know, a marginal effect point estimate, but still they allow to give some insight. Maybe I have a supplementary slide just to give an idea of what I'm talking. Oops. No, I lost the screen. Just 1 second. Okay. No, never mind. I don't have the appendix slides here. Sorry. But anyway, these type of metrics are increasingly emerging as potentially interpretable machine learning metrics that we use in this sense. And in addition to your second question, I would say that my main intuition behind that is that on the one hand, a conditioning availability, so this decision of households to purchase a conditioning is mainly a response to Long run, climate change or and changes in the income availability. So the fact that people become more affluent and are eager to have this technology installed at home to use it when they need. But then there are specific regions of the world where you have a much higher intensity of use during the year as a result of higher number of heat days, hot days, for instance. And another thing maybe that it's also explaining why you notice those areas for the consumption is that that map was showing the total consumption. So it's of course population distribution matters, and of course China, Nigeria, and India are some of the most populated countries in the world. So you can get also why those areas emerge as hotspots of electricity demand. Yeah.
Then we have Carla Schulte Fischdick, who asks if the work will be used for the topic or for the degradation of soil, I guess, instead of measuring greenness. And she also asks whether these models can be used to enable decision makers to display the possible effects of value options for actions. So as a policy support tool.
Concerning the first question, to be honest, I don't know. I think that the current model for urban green space is not suitable as it is for assessing dimensions related to the soil, because it's a model trained on canopy cover data. So it's a model that is trying to get a sense of how much green canopy there is when looking around in a street of a city. So I think that it's not biophysically tailored in any way. So I think it's probably unsuitable to get a soil indicator. So probably one would need to adapt it or derive a sibling model which is trained on some soil data. But in concern with the second question, I think totally yes, and it's probably the main reason why we try to build these models, that is to then assess different decisions and options on the policy scale, but also on the scale of individuals. So what the individuals can decide to do, such as install an air conditioning, or what the policymaker can decide to do, which is plant more trees within the city. And then perhaps the ultimate goal is to see how these two levels talk to each other. So if policymakers does something related to tree planting, then does this affect the decision of a household to purchase or use air conditioning? Just as an example.
There's a related question by G. Santinelli, who asks how our policy actions like adaptation and mitigation interventions enter the model. So not in the future, but like I think the question is, are they included? Do the models already take this into account? So perhaps you want to just spend a couple of more words on this.
Yeah, it's a good question. So they do to some extent in the air conditioning model, which is in the projections of the air conditioning models, in the sense that when we carry out projection, we consider different scenarios of RCP scenarios that are scenarios of different mitigation pathways, basically decisions, policies. So when making projections, we can evaluate the future, let's say, impact of these mitigation policies on an adaptive decision like the purchase of air conditioning. On the other hand, in the urban green space model, so far we didn't go make the step of thinking about predictions of future projections of future urban green space. So currently, it's just trying to show that you can reproduce the present situation through the use of data in a model. But when it will come, or if it will come to making projections, then we will need to think carefully how these type of decisions can be incorporated. Yeah.
There are more questions on scenarios. Anna Pagani is asking, is curious about the use of SSP or CP scenarios. Did you use data from CMIP 6 for the surface temperature? And she also asked, would it be relevant to look also at later in the century when the scenarios are more divergent? And perhaps also not only by scenario, but also by level of global warming.
Thank you for your question. Yes, we do use the CMIP6 data, the particular here, the downscaled, as we use gridded data, so the downscaled bias corrected data from a NASA GDDP, which provides different scenarios. But so far, I think one of the main reasons we decided to stop at 2050 is that the socioeconomic drivers, which are really, really important in the dimension of adaptation, have really, really large levels of uncertainty, in particular the economic growth, for instance. So we wanted to, let's say, provide some medium term projections that can be considered, in energy models, for instance, to understand what planners could do today to anticipate future boost in energy demand. But indeed, I think it's in principle very possible to extend the future horizon. Yeah. Hi, Francesco, can you hear?
Okay, so I think we have time for the very last question and just in Wanje, where the modeling at the city level. Kind of machine learning based predictive simulation would you recommend in urban and city planning? So at what level? Micro level, meso level? There's a lot of talk about city digital twins, but the simulation component is uncertain. So what do you think about machine learning for urban level planning? And Justine also wonders how much the machine learning tools can improve existing models to assess the impact of urban vegetation density. So more broadly, what do you see as the avenues of machine learning for the studies surrounding urban vegetation?
Thank you. I hope I fully got the question because it was cut a bit, but I think I did. So in my understanding, machine learning is suitable for, let's say, city level applications and something like, let's call it digital twin type of applications. However, as I was saying when answering the very first question by Francesco, I think what is crucial is to ensure that the model the data is trained with cover a wide range of setting and conditions and variability in the different variables that are considered. If we want the model to be useful for carrying out and reliable for carrying out some extrapolation out of what is the current situation in a city, for instance. So if you want to get a sense of how will a European city, Southern European city, let's say, look like in some term of, let's say, climate indicators and their impacts in the future, we might need to have a trained data set that covers a broader range of cities than just European cities. We might want to have a coverage of future conditions elsewhere where today something similar to what might be there in the future is observed. So we don't want to train a model on the city of Rome to predict the future evolution of Rome itself, but we might want to have a much broader range of conditions and data to infer what then future changes in Rome might mean by learning from other settings elsewhere that today we observe having similar conditions. This is a bit of a simplistic answer, but my answer, yes, is totally suitable, but when thinking about extrapolation, especially in the future, what really matters is this generalizability of the model. Yeah.
Okay, I think we have to close it here. So thank you very much, Giacomo, for this very insightful webinar, and thank you all for participating and joining us today. Bye-bye.
Thank you so much, Francesco and everyone.